Good morning. I am Giovanni Migliaccio and I am speaking from the University of L'Aquila, Italy. During this presentation, I will discuss the influence of friction on the dynamics of elastic systems susceptible to stick-slip motions. The presence of friction between elements forced to slide over each other may yield undesired jerking motions. This is the so-called stick-slip phenomenon. There are several situations in which this phenomenon can be observed. For instance, between the slabs of friction dampers used to mitigate vibration in buildings, or between the wiper blades and the windshield of vehicles. So there are many systems and many engineering systems in which you can observe this kind of phenomenon. The dynamic of system susceptible to a stick-slip motion, to this kind of jerking motion, is very complex. It is strongly nonlinear and it is difficult to predict analytically. So we have started this investigation considering this paradigmatic oscillating system. This is a single degree of freedom system connected elastically to a vertical support and with friction to a second horizontal support. M is the mass of the rigid block, K is the elastic constant of the spring between the block and the vertical support, C is the coefficient of the linear dashpot between the rigid block and the vertical support. Mu S and mu D are the static and dynamic friction coefficient introduced to model the frictional interaction between the block and the horizontal support. And finally, N is the normal contact force between the rigid block and the horizontal support. The system apparently is very simple, and also the equation that govern its motion are very simple. This is the equation of motion that you can obtain by using the Newton dynamic law, for instance. For what concerns the friction force, we can assume the classical Coulomb friction law. So apparently the system and its mathematical model is not complex, but it is not trivial to predict analytically the dynamics and the eventual limit cycle of this system. To understand this, it is sufficient to take a look at the possible strategy you can use to solve the problem. First of all, according to the friction law we are using, when the relative velocity between the block and the horizontal support is equal to 0, the position of the block is equal to the position of the horizontal support plus an additional constant that depend on the initial position of the system. In this case, the friction force only comes from the equation of motion, from the Newton law. In the second case, instead, when the relative velocity between the block and the horizontal support is different from 0, you have that the friction force is prescribed, and the Newton law can be used to predict the position of the system by double integration. And so in the first case, you have an analytical solution that we can call the stick solution. In the second case, you have an analytical solution you can call the slip solution. So in both the cases, you have analytical solution and you can predict the behavior of the system by considering a combination of this solution. But this not allow us to predict the long-term response of the system analytically, because you can implement this algorithm and you can assign the initial condition, you can assign the system parameter, you can perform numerical simulation and observe that the system may undergo a continuous sticking motion or a continuous sliding motion or an alternating motion in which you have sticking phases and sliding phases, like in the case reported in this slide, in which starting from a certain initial condition, you have a sliding phase, then a sticking phase, then a sliding phase, and so on. But this is just the results of a numerical simulation, and so this is not. It is not possible using this approach to predict a priori the long-term dynamic response of the system. So to study the effect of the friction on the long-term dynamic response of systems like this, we are considering a simplified version of the system. In this presentation, we will negate the influence of the internal damping. We will also assume that the vertical support is fixed and the horizontal support is moving, and it is moving according to a periodic law, like this. Using this model, we want to predict the influence of the friction on the long-term dynamic response of this kind of dynamical system. So, first of all, we studied the case in which the system is in a sticking phase. A sticking motion is characterized by this condition. The relative velocity between the block and the support is equal to 0, and in this case the position of the system can be put into a simple closed form like this. Now, by considering that we are in a sticking phase, that means this condition, this inequality is satisfied, and considering the equation of motion that is valid in the sticking phase, we can obtain this inequality in terms of the dimensionless parameter alpha and lambda. This inequality is called endless sticking condition because if we are in a sticking condition and this inequality is satisfied, the system will remain in the sticking phase. This condition is expressed in terms of non-dimensional parameter. The non-dimensional parameters that are necessary to introduce this inequality are the natural frequency of the system, the capital omega, that is the ratio between the frequency of the oscillation of the horizontal support and the natural frequency of the system. And other important dimensionless parameters introduced to express this inequality are the dimensionless amplitude A, which is the ratio between capital A and a characteristic length xs, which is the ratio in its turn of the static friction force and the K, the elastic constants of the spring between the rigid block and the vertical support. And finally, the last dimensional parameter that we need to introduce is lambda, that is associated with the initial position of the system. It is possible to express this inequality also in another form, in the form reported in this other slide. You can see here the inequality in terms of the parameter A, and which make it possible to introduce explicitly in the inequality the frequency omega. If you consider a graphical representation of this inequality, we can say that if you are in the blue region of this domain, an endless sticking phase is possible. Further detail about this endless sticking condition can be found in the paper quoted in this slide. For what concerns the sliding motion, the endless sliding condition is this one. It can be found in this paper, in the paper quoted in this slide. Anyway, the solution during the sliding phase is simple to obtain. During the sliding phase, we have that the friction force is equal to the dynamic friction force. And during the sliding phase, a sticking phase can begin only if the relative velocity goes to 0 and the friction force required to start a sticking phase is not greater than the dynamic friction force. In such a case, if this condition is not verified, so if the friction force is not smaller than the dynamic friction force, then the sticking phase cannot begin, and then the block continues to slide with respect to the moving support. Analytically, this can be expressed by the inequality called in this slide endless sliding condition. By using this inequality, it is possible to study the existence of a sliding limit cycle. For instance, a possible limit cycle that we have studied, we have found, is this one. It is a sliding limit cycle in which the position of the block is equal to 0 at a generic time instance and at after half period and after one period since that time instance, and at the same same time instance, also the relative velocity between the block and the rigid support is equal to 0. So a limit cycle characterized by this condition, a sliding limit cycle that satisfies this condition, is possible only if this inequality reported here in the red box is satisfied. It is useful to report this inequality into the domain alpha omega, and so the graphical representation reported here are for 3 different values of the eta parameter, which is the ratio between the dynamic and static friction coefficients. So in this graphical representation you can see for these 3 different values of eta. If you are in the red regions, you can say that an indefinite sliding is allowed. If you are in the blue region, you can say that an indefinite staking instead is allowed. This does not mean that other kind of limit cycle, for instance, other types of sliding limit cycle are not possible. This only means that these 2 types of limit cycle are possible if you are respectively in the red region or in the blue region. We have also performed some numerical simulation to validate the analytical finding of the present investigation. For instance, starting from homogeneous initial condition and considering a parameter A equal to 10 and a parameter eta equal to 1/3, we have performed a numerical simulation by varying the values of the frequency omega. So we move from the point in the region number 1 to the point in the region number 2, then we continue to increase omega and we are in the region number 3, then in the region number 4, and finally in the region number 5. In this other representation in which we have reported the position x at which the relative velocity between the block and the support vanishes, we have in the first region that stick-slip limit cycle are possible. We find stick-slip limit cycle in the first region, as it is expected by taking a look at this domain, because in the first region you cannot have endless sliding and you cannot have endless sticking motion. Instead you have slip limit motion in the region number 2, stick slip limit motion in the region number 2, again slip limit motion limit cycle in the region number 4, and stick limit cycle in the region number 5. We have performed a similar analysis for other value of the eta parameter, and we can say that also in this case the results that you can perform, what you can say by taking a look at the analytical map reported in the left, is actually what you get by performing numerical simulation, as it is observed by taking a look at the picture on the right in this slide. We have also performed the numerical simulation. We have observed the time history. So in the region number 1 we have a stick slip limit cycle. In this region instead we have a sliding limit cycle like this. In the last region we have a sticking limit cycle like this. So the numerical simulation confirmed the analytical findings. Just to conclude, during the presentation, I have focused the attention on a paradigmatic 1 degree of freedom system that is connected elastically to a fixed support and with friction to a moving support. An analytical approach has been used to study analytically the problem and to study the existence of a certain kind of limit cycle, and it is found that a small subset of characteristic parameters of the system can be used to fully characterize the long-term dynamic response of the system. They are the parameter A, omega, and eta. And the analytical finding of the investigation have also been validated by performing numerical simulation, and excellent agreement has been found between the analytical and the numerical results. So thanks for your attention, and if you have any curiosity, I'm here. Thanks again.